Hello! Thanks for watching, and welcome to the next video in my series on basic statistics. Now, as usual, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, but you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can work through it. I have faith in you. Many other people around you have faith in you. So should you. Number two, please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way, when I upload a new video, you know about it. And it's always nice to connect with my viewers online. I feel that life is much too short and the world is much too large for us to miss the chance to connect when we can. Number three, if you like the video, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist. That does encourage me to keep making them for you. On the flip side, if you think there's something I can do better, please leave a constructive comment below the video, and I will take those ideas into account when I make new ones. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'm just going over basic concepts, and I will be doing so in a slow, deliberate manner. Not only do I want you to know what is going on, but also why and how to apply it. So, all that being said, let's go ahead and get started. So this video is the next in our series about analyzing variance. In our last video, we discussed how to construct confidence intervals for the variance. Now, this video is about conducting hypothesis tests for the variance. For this type of problem, we will test whether or not a sample variance meets the assumption of a hypothesized variance. For example, a business analyst or quality assurance manager may set a goal of maximum acceptable variance in some process or to test to see if a process is meeting a predefined industry standard. We can use this method to test whether or not the sample variance meets or fails to meet that goal or standard. Now, of course, variance plays an important role in fields such as quality assurance and operations management. Ever heard of Six Sigma? Well, you probably have. Well, what is sigma? Well, sigma is the symbol for population standard deviation, which of course is the square root of the variance. Now, central to Six Sigma and things like it is the monitoring and reduction of process variance. For example, a quality assurance manager for Samsung or Apple may want to set and then test the variance for smartphone battery life. An investor may want to set a variance limit on a stock's average return in order to avoid too much risk. Now, I do want to be honest with you. This topic is not easy, but I will go slowly and use concrete, real-world examples to guide you along, but you may need to pause the video now and then to let what you're learning sink in a bit before moving on. So, let's go ahead and get to work. So we'll start off with our first example. This is high interest realty. So high interest realty has set a timed sales goal whereby the standard deviation of the listing of a home to selling the home, that time frame, is no longer than 21 days. So they want a standard deviation of 21 days. Now, since the standard deviation of 21 is the square root of the variance, 21 squared, or 441, is the variance upper limit. Now, realizing this goal will help with sales forecasting and marketing. So to conduct this analysis, the sales records for 15 previously sold homes were randomly selected. Now, based on the sample, the following information was obtained. So our sample size was 15. The mean sell time was 162 days. The variance was 582. And the standard deviation was 24 days. So we can see here we have a mean, and really for this type of analysis, we're not that concerned with the mean because we're focusing on variation. We're focusing on the variance. Now again, S squared is the sample variance, that's 582, and the sample standard deviation is 24 days. Now looking at that, we can see that the standard deviation of 24 days is higher than the goal of 21 days they set above. But remember, because we're using a sample, there's going to be some error involved. It's going to be over an interval. So we will have to see whether or not that standard deviation, and of course the variance, exceeds it enough to be significant. The single sample hypothesis tests for variance follow the same patterns as those for means. So in this first case, our null hypothesis says the population variance sigma squared is equal to our hypothesized population variance, which is sigma squared sub 0. Now, if we reject that null hypothesis, the alternative says that they are not equal. Now, of course, this is a two-tailed test, and remember, we're using the chi-square distribution. In this case, the variance could be above or below our hypothesized if we do reject the null. Now in the second case, our null says our population variance is less than or equal to our hypothesized population variance. Of course, if we reject that, then we will proceed to our alternative that says sigma squared is greater than sigma squared hypothesized. Now, of course, this is an upper or right-tailed case because our alternative points to the right. Now the final type is where our null says sigma squared is greater than or equal to sigma squared hypothesized. Therefore, the alternative is that it's less than the hypothesized. So this is a lower-tailed test. Now, I want to point out that this last case, where we're looking in the lower tail, is very seldom used. We mainly focus on the left two, where we're interested in if it's equal or not, or in the middle, our population variance exceeds some hypothesized value. Now, one thing I can think of in the right case is sort of an example I used a video or two ago, where an employee was writing down the same number over and over again for a measurement. Now, if someone writes the same number over and over and over again for a measurement they should be taking using a piece of equipment, they will have a variance at or near 0. Because someone writing the same number over and over and over again, those same numbers will create a variance of 0. But in these type of problems, we're usually focusing on the left two. So we're going to do an example of each in this video. So let's go ahead and look at the two-tailed hypothesis for sigma squared, the population variance. Now remember, we're using the chi-square distribution. So we're going to set an alpha level of 0.05. So we're talking about the middle 95% of this chi-square distribution. So that means we have 2.5% in each of the tails. So in the middle, that is our non-rejection region. So if our test statistic falls in that blue region, we will then fail to reject the null hypothesis. So we can label this region like this. Now don't freak out. Some of my students I work with, when they see subscripts, they kind of freak out. But all this is saying is that this blue region is between these two chi-square endpoints. So let's look at the one on the right first. So we have chi-square sub alpha over 2. Well, what is our alpha? Our alpha is 0.05. So 0.05 divided by 2 is 0.025, or 2.5%. On the left-hand side, we have 1 minus alpha over 2. So in this case, it's 1 minus 0.025, or 100% minus 2.5%. That's all that means. So our chi-square value here in the middle is between a chi-square of 0.025 probability here in the lower end and a chi-square with 0.975 cumulative probability here on the left-hand side. This is just setting the ends of our non-rejection region. So we can go ahead and label those on the axis below. Now the critical values are found in the chi-square table for the proper degrees of freedom. So remember, each chi-square is different. It depends on the sample size and therefore the degrees of freedom. So we will go into the chi-square table, find these probabilities in the chi-square table for this alpha level with that degrees of freedom, and that will actually tell us the values that fall on these endpoints. So let's go ahead and look at the one-tailed cases. So here we have an upper tail. So in this case, the chi-square value, the blue region, is less than or equal to the chi-square at this alpha level. So remember, our alpha level is 0.05, so this brown region is 5%. Now what about the left side? Same idea. So here chi-square, the blue region, is greater than or equal to chi-squared 1 minus alpha. So our alpha is 0.05. So here we have chi-square is greater than or equal to a chi-square value at a cumulative probability of 0.95. So that is here. So again, the critical values are found in the chi-square table for each degrees of freedom. Now we know that the sampling distribution of the variance follows this chi-square distribution. But how does that relate to the actual data we collect? Now whenever a random sample of size n is selected from a normal population, the sampling distribution of chi-square follows this expression, where n is the sample size, s squared is the sample variance, and sigma squared is the population variance, which of course is unknown. And this has a chi-square distribution with n minus 1 degrees of freedom. So let's actually go back to our problem and solve it. So the first thing we want to do is establish our hypothesis. So remember, the upper limit for the variance in this problem was 441. So our null hypothesis says that sigma squared, the population variance, is less than or equal to 441. That's representing our upper limit. Lower than that is great, but that's our upper limit. Therefore, the alternative hypothesis is that our population variance is greater than 441. So next, we'll determine the appropriate statistical test and sampling distribution. So this will be a one-tailed test. Since the concern is a larger than desired variance, it will be an upper or right-tailed test. Now we will use the chi-square distribution with 15 minus 1, that's n minus 1 degrees of freedom, so 14 degrees of freedom. And of course, this is our chi-square calculation, our test statistic. So our significance level is 0.05. We already talked about that. State our decision rule. So if the chi-square is greater than 23.685, we reject the null hypothesis per the chi-square table. So if we went to our chi-square table, we looked up an alpha of 0.05 with the degrees of freedom of 14, we will find that this critical value is 23.685. And of course, if our test statistic is above that, that places it in the upper region, in the brown region, and therefore we would reject the null hypothesis. So gather our data, which we already did. So our sample size was 15, and our sample variance was 582. So remember, the goal is 441 for the variance, but our sample had a variance of 582. Now that is higher, but the question is it significantly higher than we would expect due to normal random variation? Let's go ahead and calculate our actual test statistic. So here's our chi-square expression, and here is our data over here on the right. Now here we have 15 minus 1, so that's 14, times 582, that's our sample variance, and then 441 is our hypothesized variance. Now in some cases that will be unknown, but in this case, because we're testing it against a hypothesized variance, it is known. So I want to be clear there. So our hypothesized variance is 441. Now we go ahead and do that calculation, and we come up with a chi-square value of 18.48. So here's all the information we have so far. So we have our hypothesis up there at the top. We have our chi-square with 14 degrees of freedom here on the graph. We have our 95% non-rejection region on the left-hand side in the blue. Then we have our rejection region in the brown on the right-hand side, and that's separated by our critical value we found of 23.685. Now, our chi-squared value, our test statistic, was 18.48, so it falls right there. So our conclusion is that we fail to reject the null hypothesis. The sample data does not offer sufficient evidence to conclude that the listing to closing time variance exceeds the upward limit set by high interest realty. So yes, our sample variance of 582, I think it was, is higher than 441. But remember, we're using a sample variance, so we expect some natural variation in our samples. So even though it's higher, it's not high enough to be beyond what we would expect due to just simple random sample variation. So let's look at example 2, micro machines. A new precision machine tool is being installed in a local production plant. Based on laser read measurements, the machine being replaced produced a tooling variance of 100 microns. So S squared, 100 microns. So after a break-in period, the new machine is tested to see if its production variance is the same as the previous machine. So 30 samples are taken from the machine, producing a sample variance of 162 microns. So our goal, or our hypothesized variance, is 100 microns. The new machine produced a sample that had a sample variance of 162 microns. Now we know that that is higher, but again, the question is it high enough to be statistically different? So again, here are the different ways we could formulate our hypothesis. Now we're going to use the one on the left, because remember, we're testing whether or not the new machine produces a variance that matches the old one, which was 100 microns. Now it could be higher, it could be lower, but it depends on what our sample tells us. So let's establish our hypothesis. So our null hypothesis states that the new machine's population variance, sigma squared, equals 100 microns. Therefore, the alternative is that it does not equal 100 microns. Now this would be a two-tailed test, since the new variance could be lower or higher. Now we will use the chi-square distribution with 30 minus 1 degrees of freedom, because remember our sample size is 30. And again, here is our test statistic formula. So our significance level will stay at 0.05. Now we'll state the decision rule. So if our chi-square is less than 16.047, we will reject our null hypothesis. If it is above 45.722, we will also reject our null hypothesis. So it looks like this. So with 29 degrees of freedom, the critical value on the left is 16.047, and the critical value on the right is 45.722. So that sets the ends of our 95% interval there in the middle. So we gathered our data, and of course n equals 30, and s squared equals 162, our sample variance. So calculate our test statistic. So n is 30, s squared is 162. Our hypothesized variance is 100. So we go ahead and substitute everything back in. So we have 30 minus 1, 29 times 162, all divided by 100. So that generates a chi-square value of 46.98. So here's everything we had before. You can see we have our critical values of 16.047 on the left and 45.722 on the right. Now our test statistic, our chi-square value, was 46.98. And look at where that falls. It falls in the upper rejection region. So our conclusion is we reject the null hypothesis. The sample data does offer sufficient evidence to conclude the production variance of the new machine is higher than that of the previous machine. So we may need to recalibrate or repair the new machine. So an important note here, keep in mind that we're not saying anything about the means of these processes. In the high interest realty example, the mean time to sale could be way off goal, but the target variance could be on goal. So think about producing a 95 millimeter meter stick, which is wrong. It should be 100 millimeters. Producing a 95 millimeter meter stick, but doing so very consistently. Now in the micro machine example, the new machine could be producing on average the exact specification we want. But the problem is it's doing so inconsistently. So think of producing on average 100 millimeter meter sticks. But some are 70 millimeters, others are 130 millimeters, some are 80 millimeters, other ones are 115 millimeters, but on average, they're 100 millimeters. Well, that's not right either. So you have to think of these two things that are going on. The mean of the production process, or whatever it is you're looking at, and then the variance, which of course is the spread, or the width of the distribution. So let's look at this in an actual little chart I made. So if we're looking at the quality or monitoring the performance of some process, we can think of these two things. Is the mean on target? That's up there at the top. Is the variance on target, which is over here on the left? Well, if both are good, if the mean's on target, so yes, if the variance is on target, yes, then we're doing good. Both are right on target, and we just keep monitoring. But let's say the mean is off target, so no, but the variance is. So in that case, we would try to fix the process mean, because the variance is okay. So the width of the distribution is correct, but its location side to side is wrong. Now let's look at the case where our mean is on target, so that's good, yes, but our variance is off target. So in that case, we would fix the process variation. So the mean is in the correct place, but the variance is way off. Usually it's way too high, so the distribution is too wide. We have too many products that are being produced out of our specification. Now, of course, if both are bad, if the mean is off target and the variance is off target, then that's going to be like a crisis. So we're going to have a meeting and determine how we can fix it. So think of the meter stick manufacturing example. So if the mean is on target and the variance is on target, so green, we're consistently producing meter sticks that are 100 millimeters. So they're the proper length, and we're doing so consistently. Now let's look at the mean as off target. In that case, we're making 95 millimeter meter sticks very consistently. So we're doing the wrong meter stick consistently. Now what about if the mean is on target, but the variance is off target, down here in the lower left? Well, we're producing meter sticks that are on average 100 millimeters, which is good, but we're doing so inconsistently. So their lengths are all over the place, but when we average them out, they're 100 millimeters. Now, of course, if both of them are off, then we just have a basic mess. We have a bunch of sticks that aren't the right length, and they don't even average out to 100 millimeters, and we have a problem. So you always want to think of these two things that are going on. Now, of course, we're focusing in this video on the variance. But when we get to ANOVA, the analysis of variance, we'll be looking at both of these. So we will be looking at where each factor's mean is and each factor's variation. We'll be looking at both of those things. So we've looked at the mean in the many previous videos, and now we're looking at the variance in these videos, and we will put them both together when we talk about ANOVA later on. So that wraps up our video on hypothesis test for the variance. Now remember, usually what happens in these sort of scenarios is that we set some goal. Either that's a goal our company makes or it's some industry standard for the variance. Then we test whether or not our production is meeting those goals or standards. Most of the time, we use a two-tailed test or an upper-tailed test. Lower-tailed tests do exist, but they're very infrequent. So just keep in mind what we're looking at here is the spread of our data, which in the real world can mean many things, from the variation of our produced goods, or the risk of a stock, or the time it takes to do something. So remember, if you're watching this video because you're struggling in a class, stay positive and keep your head up. You are a smart, talented, amazing person. Never let anyone tell you any differently, including yourself. Please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. It's always nice hearing from you. And finally, just remember that the fact that you're on here, trying to learn, trying to improve yourself as a student or a business person, that is what really matters. I firmly believe if you have the right learning process in place, the results will take care of themselves. So thank you very much for watching, and I look forward to seeing you again next time.